Hello, welcome to another module in this massive open online course on Bayesian MMSE estimation for wireless communications. Alright, so far we have looked at the MMSE, that is minimum mean squared error of a wireless sensor network. Let us look at the MMSE, that is a minimum mean squared error of a for the wireless channel estimation problem, and the analysis is going to be similar with some slight modifications for the complex channel coefficient estimation case. Alright, so just for the sake of completeness, let us look at the MMSE, that is a minimum mean squared error of wireless channel coefficient estimation. Okay, so what we are going to look at in this one, although it is going to be similar to the wireless sensor network, MMSE of wireless channel estimation. Okay, and where we know that this term MMSE, this stands for the minimum, this is the actual minimum mean squared error. This is the actual minimum mean squared error. Of course, we have y bar equals, let us look at the model for the estimation. Let us consider the transmission law. Of course, we have looked at this model, but let us just recall this model. Let us consider the transmission of n pilot symbols, and therefore, I can stack the received symbols as a vector, that is y1, y2, so on up to yn. This is the received or the observed vector, which is equal to your pilot vector comprising of the pilot symbols x1, x2, so on up to xn times h, which is the channel coefficient, plus the noise samples, of course, V1, V2 and Vn. So, we are considering the transmission of n pilot symbols x1, x2, xn, which we are making as the pilot vector x bar, the corresponding n received symbols y1, y2, yn, which basically forms the received vector y bar, right, and the noise vector v1, v2, vn, which forms the noise vector v bar, and of course, the channel coefficient h. Okay. So, the system model for the estimation is basically you have your vector y bar, this is the observation vector, this is your pilot vector, and this is the v bar. Which is your noise vector, and this is basically your channel coefficient h, alright, and estimation of this channel coefficient h is termed as wireless channel estimation. Okay, this is something that we already seen. Now, what we are going to do is, let us first start with the scenario where the channel coefficient h is a real quantity, and later we will see how the results can be modified for the scenario where the channel coefficient h is a complex quantity, that is known as a complex feeding channel coefficient. Alright, so first let us start with the real scenario. Okay, and therefore, our system model, we have y bar equals x bar, this is something that we have already seen, x bar h plus v bar, and the MMSE, that is the minimum mean squared error, which is equal to the expected value of magnitude of h hat minus h whole square, well this is equal to RHH minus RHY into RYY inverse into RYH, correct? Okay. And we know, remember we are considering a channel coefficient H to be Gaussian, right? The prior distribution is Gaussian, correct? With mean mu h and variance sigma h square. So, our RHH, this is equal to your prior variance, this is sigma h square, which is nothing but the which is basically your prior variance, all right. So, we already know RHH, that is expected value of h square, expected value of h minus mu h square equals sigma h square, which is the variance of the prior, the Gaussian prior for this feeding channel coefficient h. Okay. Similarly, we have also derived these quantities and you can recall them, RYY, which is equal to expected value of, in fact, y minus, in fact this expected value of y bar minus mu bar y times y bar minus mu bar y transpose, and this quantity is equal to sigma h square times x bar transpose plus sigma square times the identity matrix. Okay. This is something that we have already derived, all right. Please check again, if you are not clear about this, please check from the lectures of the previous modules. And we have the cross correlation, that is RHY, which is equal to also RYH transpose. So, remember we are similarly considering, we are still considering the real scenario. So, RHY equals RYH transpose. If it is complex, then it will in fact be the Hermitian, correct. So, we are still considering the real scenario. So, this will be sigma h square x bar transpose. Okay. So, these are the three different quantities, RHH, RYY, in fact 4 different quantities, RHH, RYY, RHY and RYH, and RHY and RYH are the transposes of each other. Okay. And now therefore, the MMSE can be given as, therefore, we have the MMSE therefore, the MMSE is, you have expected value of h hat minus h square, this is equal to the MMSE, that is the minimum mean squared error, that is equal to, now substituting these quantities, RHH sigma h square minus RHY, that is sigma h square times x bar transpose. So, this is basically your RHH, this is your RHY times, remember RYY inverse, that is sigma h square x bar transpose plus sigma square identity inverse, this is R YY times x bar into sigma h square. So, this is your R Y H. Okay. So, this is your expression, basically this is the expression for the MMSE. So, let me just write it down once again over here clearly, that is basically sigma h square minus sigma h square into x bar transpose sigma h
square x bar transpose plus sigma square identity inverse times x bar into sigma h square. Okay. So, this is your MMSE. Okay. So, this quantity over here, okay. So, this quantity is basically your MMSE, that is the minimum mean squared error for the estimation of the channel coefficient H. Okay. Now, we are going to simplify it, and we are going to simplify it, and you already know the principle that we use in simplification. We are going to employ a simplification for this, and we have already seen this part can be interestingly simplified as, you can recollect again from the previous modules, that sigma h square times x bar transpose, we have demonstrated this also, x bar transpose into sigma h square x bar transpose plus sigma square times identity inverse. This is equal to sigma h square x bar transpose x bar plus sigma square inverse times sigma h square x bar transpose. This is something that we have already shown, and now you can see this is a scalar quantity, sigma h square x bar transpose x bar, this is a scalar quantity, because x bar, remember we justified this, x bar transpose is a row vector, x bar is a column vector. So, x bar transpose x bar is a scalar quantity, that is in fact norm x bar square. So, there is sigma h square norm x bar square plus sigma square, which is a scalar quantity. So, the inverse of this scalar quantity will simply be its reciprocal. Okay. So, this is basically, this is equal to, this follows in fact from several principles. We have proved it in one of the modules. In fact, this also follows from the matrix inversion lemma, and you can derive it again, the matrix Woodbury identity or the matrix inversion lemma. Okay. And therefore, this is the simplification, and now using this, so now we will use this, let us call this star, this quantity is also star. Now, we will simplify this, now we will simplify the MMSE by substituting the simplification for this quantity star derived above. So, this is equal to sigma h square minus sigma x square x bar transpose divided by sigma h square norm x bar square plus sigma square into x bar sigma h square, which is equal to sigma h square minus sigma h to the power of 4. Now, you see you have x bar transpose times x bar, that will give a norm x bar square divided by sigma h square norm x bar square plus sigma square. And in case you are wondering, norm x bar square is nothing but this quantity is nothing but, just to remind you, norm x bar square, this quantity is nothing but the row vector x1 x2 xn times the column vector x1 x2 xn, okay, and this will be equal to your x1 square plus x2 square plus so on plus xn square. And later when we consider the complex scenario, all you have to do is you have to replace this x1, x2, xn by their conjugate. So, this will become x1 bar or x bar Hermitian, this will still be x bar, this is for the complex case. Remember, for the real case, of course, complex conjugate will yield the, so this is for the complex case, and this will then be magnitude of x1 square plus magnitude of x2 square, so on up to magnitude of xn square, and this is the quantity we are calling nothing but norm x bar square. So, norm x bar square for the real vector x bar is x1 square plus x2 square, so on up to xn square. For a complex vector, that is vector with complex pilot symbols, complex entries, this is simply magnitude x1 square plus magnitude x2 square, so on up to magnitude xn square. That is the only difference. Okay. And now therefore, you can simplify this part, you can simplify it, just carry forward from where we have left off. That will be given by now you can taking this common sigma h square times norm x bar square plus sigma square sigma h4 norm x bar square plus sigma square sigma h square minus sigma h to the power of 4 norm x bar square, and this you can see the sigma h power 4 norm x bar square, sigma h power 4 norm x bar square, these things cancel, and what you are left with is basically you are left with sigma h square divided by sigma h square norm x bar square plus sigma square. And now, alright, we have this expression. Now we divide by this quantity, divide numerator and denominator by sigma square comma sigma h square, and this when you divide numerator and denominator by sigma h square, what this will give you is, of course, numerator will become 1, the numerator will become 1, denominator will become norm x bar square divided by sigma square plus 1 over sigma h square. You can verify this, and now what I am going to do, I am just going to rewrite this as follows. I am going to bring the norm sigma square to the denominator, and that can be written as 1 over, and this you can see interestingly can be written as 1 over sigma square divided by norm x bar square plus 1 over sigma h square. Okay. And now this expression, by the way, realize that this expression is also valid for the case where the channel coefficient h is complex. Alright, all you have to derive substitute is basically substitute norm x bar square by magnitude x1 square plus magnitude x2 square, so on up to magnitude xn square. Alright, we already said that. Okay. Now observe, so let me make a note of that. This is also valid for the complex coefficient h. This is also the MMSE for the estimation of a complex channel coefficient h. So also valid for a complex and now you can see what is this quantity. Again, this quantity is the MSE of the or mean square error of the maximum likelihood or ML estimate and this quantity is the variance of prior,
that is H is Gaussian channel coefficient with mean mu h and prior variance sigma h square. So, this is basically, now you can see the harmonic mean, this is the harmonic mean, this is equal to of MSE mean squared error of MLE, that is the ML estimate comma the prior variance. So, this is the harmonic mean, or basically you can also say the HM, right. Harmonic mean is nothing but, basically just abbreviate this as HM, the harmonic mean of the MSE of the maximum likelihood estimate and the prior variance. Okay. And remember, this is also valid for a complex channel coefficient H, except for a complex channel coefficient, instead of H hat minus H square, you have to look at magnitude H hat minus H square. So, this is the for a complex, specifically for a complex, of course this is valid for a real also, real coefficient H also, you have to simply look at expected value of magnitude H hat minus H whole square. And what we have seen is that the net variance is the harmonic mean of the variances of the ML estimate and of the prior variance. And of course, all the insights we have drawn for the wireless sensor network case are also valid. For instance, the harmonic mean of two quantities less than each of the quantities, right. So, the harmonic mean of the variance of the ML estimate and the prior variance is less than both the variance of the ML estimate and also less than the prior variance, alright. So, by combining the information from the observations and also basically the prior information, you are getting an estimate which has a lower variance than both the ML estimate, which is derived simply from the observations, the prior mean, which is derived simply from the prior. So, by combining these two in an MMSE fashion, you are able to get a variance which is lower than both. And of course, the other intuition is also valid, which is, let me again remind this for the sake, I mean at the risk of being repetitive, the MMSE equals 1 over MSE of ML plus 1 over the prior variance. If the MSE of the ML estimate is very close to 0, is very small, then the dominating term in the denominator, you can observe 1 over MSE of ML will be very large, because MSE of ML estimate is very small. So, the denominator will be dominated by 1 over MSE of ML. Therefore, 1 over MSE of ML will simply be the MSE of ML. Okay. So, this term, so at if MSE of ML is equal to 0, so you can have again two cases, MSE, that is when the MSE of the ML estimate tends to 0, that is ML estimate is very accurate, and this happens when n tends to infinity, number of observations tends to infinity, this approximately tends to the MSE of ML estimation. Now, if on the other hand prior variance is very small, the prior variance tends to 0, then again the denominator is dominated by 1 over the prior variance, right, and therefore this tends to, this is approximately equal to simply the prior variance. Okay. So, that you can see, these are the interesting insights, again very similar to the wireless sensor network scenario. You can see the observation, large number of observations, which means the ML estimate is very accurate, its variance is very low. So, naturally the estimation error, the final MMSE estimation error will be very close to that of the MSE of the maximum likelihood estimate. On the other hand, if the prior variance sigma h square itself is very small, which says that you know H to begin with to a very high degree of accuracy, because sigma h square is very small, then the denominator is dominated by 1 over sigma h square, and the entire expression will become approximately sigma h square, that is very similar to the MMSE of estimation, is very similar to the prior variance. Alright. So, these are the two special cases, and of course, for different levels of relative accuracy of the ML estimate versus the versus the prior variance, I mean you get the combination which is in fact the harmonic mean of the MSE of the ML estimate and the prior variance, which is in fact lower than each of these quantities. Alright. So, that is the interesting aspect of it, and we will start with here and we will stop here, and in the next module we will see briefly what happens when this channel coefficient H is complex, what is the interesting observation there and what is the interesting interpretation specifically for the scenario when the channel coefficient H is complex. Alright. So, we will stop this module here. Thank you.